Okay, today's lesson will be focused on Faraday's law and Lenz's law. I will definitely go through Faraday's law, but it depends on time constraint whether I'm able to go through Lenz's law, but definitely Faraday's law. I'm going to make certain assumptions. I'm going to make the assumption that you still remember F equals to B, F equals to for wire and for charge particle. What's the expression for the force on a wire and on a charge particle? BIL sine theta. Good. And given any wires, you have this, this, and this. This is your B, this is your I, this is the theta, right?
No.
Theta is wrong.
Remember, this is actually the theta. Can? Now, then this one, the QV and sine theta. Cool. And the theta is the angle between the velocity and the B field. And I went through with you this left hand rule and the right hand slap rule. You still remember? The right hand slap rule. Okay, now let's try out. Let's give you 3 scenarios and see whether you still know how to use the left hand rule or your right hand slap rule. But remember that in IB, only left hand rule is recognized. Okay? So whichever works, but in exams, left hand rule. So let's try. This is B, this is I, this is B, this is V, and this is V, and this is V. First one, all you need to tell me is the direction of the force.
Going up.
Don't
down.
say it. Just keep it to yourself, and then with time when I ask you to give the answer, so that your friends got time to think. And first one. Okay, in your mind there should be an answer already. Yeah? Let's check. How many of you say there are 6 cardinal directions? Up, down, and right, left, in, out. So which one is it? Down, right. So this one points here, this one, and then this way. Okay? Quite easy, yeah? Second one. What's the direction? Excellent. I purposely didn't put it in the charge. Yeah? I purposely didn't put it in the charge. I was waiting for someone to ask a question. Because you need information, alright? I was waiting for someone to give you an answer. Then if you are wrong already, you give me an answer. So I want to make your life a little bit more difficult. I mean, so that's the first test. You need to know the charge. Make it a habit. Second point, you need to use something, concept.
This is weird. This is very weird.
Out. Okay, that's. Now remember that whenever you do B field, I told you this last year, that you always think a long word starting with B. Perpendicular, correct. So this one is B perpendicular, this one is B parallel. So you only consider this. Always think perpendicular, very important. You find this a very important feature in Faraday's law, so always think perpendicular. So your field points this way, and current points this way, so it goes out. Cool? This one? In, out, left, right, or up or down?
It's
Correct. Don't have.
It's not
Okay. In this case, an answer, if you say an answer in the 6th one or the 6th one, it's the wrong answer. The answer is no answer. There's no force. Not like there's no answer, but no force. Okay? So, what I wanted to bring across to you, some learning points, important learning point, is that you have to know the charge for the particle. You need to know the charge first. Make it a habit. Because positive, negative makes a difference. Okay? And then you need to think about perpendicular field. And one case you need to remember is that whenever it's parallel, current and speed parallel, B field, 0 force. It must be second nature. Yes.
Are we resolving the B field in the second case?
For which one? Second case or sixth case?
Yeah.
Yes, we're resolving the B field. Yes.
So the B field can point in any direction.
The B field can point in any direction, but we always take the perpendicular component to the current or the velocity. That's the one that creates the force. And because of this, we also mentioned that if it is parallel, there's no effect. So I can have a moving charge particle. Inside a magnetic field, but no force at all. Not possible in gravitational field. Not possible in electric field. Electric field, once you move through electrical charge, move inside E field, regardless of where you point the E field, where you point the velocity, there will be a change in velocity. Okay? So B field is quite unique in the sense. You can have a charge particle moving in the B field, but no force. Cool? Can? Okay. let's move on now. Let's use this and develop it to Faraday's law. You see quite an interesting development.
Current direction is negative charge in direction.
Negative charge, you point the current in the opposite direction.
Oh,
Yeah. I did mention this before, right? Since we know electrons are the one responsible for electrical current, why do we still define conventional current? Because we're lazy to change. Because in the past, seriously, because in the past, before they know that electrons exist, they thought that positive charges are going to move, so they define it. And when they realized that, you must understand that in the past they don't have Facebook and Instagram. To communicate this to other parts of the world, it probably take 5 years ago. Now you just send email. All scientists. It's so much easier, right? I don't know whether there's all scientists email group, but you know.
Now can change.
No, they're changing conventions. Even 1 kg, I think they're defining it not by the mass in somewhere in Paris.
No.
Yeah, they're defining it based on certain basic quantities, like constants H. Yeah, they're defining it differently already. Seconds is defined in terms of not pendulum, but it's defined as the oscillation of a cesium atom. Yeah. So it's defined based on natural, unchanging phenomena. It's no longer that one mass really. You'll be surprised, you're going to read up on the internet, how that one mass, you think it's just one mass, that mass over there. Imagine everything is measured based on that. Gold is measured based on that. Imagine your gold that you buy, you think it's 1 kg, but actually it's 0.999 kg.
They say,
And then you don't buy 1 kg of gold. For people who buy gold, they buy by tons and sometimes. So you actually think you use $1 million to buy the gold, actually you only get $990. So everything is measured against that thing. It affects transaction. Time, it affects navigation. Yeah, so it affects a lot of things, not just time and place. Yeah? Think about it, it's very interesting. I'm going to read out on that. But that's not the focus on here. So what I want you to think about is this. I'm going to slowly develop you to Faraday's law, so you must follow me really closely. And for those of you who are in front of the camera, just check and see whether it's running. If it is not running, let me. Now, can you see that if I have a rod with a negative charge, with negative charges over here, and I pull the rod this way, do you agree that the electrons over here is also moved this way? Agree?
yeah.
Now, which means that the electron's motion towards the right constitutes the current towards the left. Make sense? Now, can you use your left hand rule and tell me what's the direction of force on this
Up.
guy?
Up,
Magnetic force.
up,
Up, down,
up.
up or down.
It's quite
No win-win situation here. It's either up or down.
It's up.
Okay, this is confusing. When it says up, means is one says down. Okay,
No,
so
it's
up or down.
It's up.
First of all, check out. Are you using the correct hand or no? So you use the right hand. Right hand is the wrong hand. Left hand is the right hand. Okay, so your current point this way. Your point this way. Down. Correct. I think you pointed in the opposite direction.
Oh.
Yeah. So the magnetic force is down. So what happens to the electrons up here? They will all be pushed down. Yeah. So then they will get pushed down, and then the bottom parts get infinite amount of charges. Correct? No? So a lot of negative charge over here, a lot of positive charge over here. So there will be infinite amount of charges of both ends if I can't continue moving this particle. Correct?
Sorry, what?
Does nature love infinity? Does nature love infinity? Actually, nature, for some reasons, nature doesn't love high energy. Nature doesn't love infinity. Doesn't love. Let me give you an example. Simple harmonic motion. If you just push something, technically at the driving frequency equal, when driving frequency equals to the natural frequency of the object, it should oscillate and absorb energy infinitely. But it doesn't. Anything in this world that oscillates will go through some energy dissipation, be it air resistance or whatsoever. It doesn't love infinity. So it doesn't go to infinity, but the question is why? So let's take a look. You've got this negative charge experiences a B field. What will these negative charges over here do to this?
Oh, is equivalent to an up current.
It will be a electrostatic force of repulsion.
Oh,
So there'll be some point where there'll be equilibrium, right?
going left.
Make sense? Yeah. Okay, so let's understand this concept. So do you agree that the equilibrium is where Fe equals to Mt? Yeah. So this one, from what we learned just now, obviously this is not dQe. The magnetic force is dQe, right? The electric force, can you see that this is almost like a parallel plate, where the particle is between the two plates. It's something like a parallel plate, yeah? So which is Q electric field. And this E, remember for parallel plate, it is divided by the potential difference divided by the separation between the plates.
Yeah.
Yes. Okay, and Yes, of course you remember. Now, boom, boom, delta V is equal to B. Now, remember in your secondary years that when you have a rod cutting magnetic field, the EMF induced depends on the speed, depends on the length, depends on the magnetic field. Now, this is the equation that you didn't learn in year 4. Now you see how it is being derived. I'm not just showing you this, I'm showing you based on fundamental principles and things that you have learned. Based on fundamental principles of equilibrium and things that you have learned previously about magnetic field and electric field separately. Now I'm just joining the two together. There we have an equation. But we are not yet at Faraday's law yet. What is Faraday's law?
Don't know.
How? 1 year ago, just 1 year ago, 2 years ago. The EMF induced is directly proportional to what?
Rate of change of magnetic flux linkage.
Linkage. Okay, wow. Looking at the notes. But at least you're looking at the right page.
Yeah.
That's good. Yeah. Some people don't even know what to look at. And so the EMF is directly proportional to the rate of change of magnetic flux linkage. What on earth is this? How does this look like magnetic flux linkage? No worries. Relax. We'll go to that later on. Okay? But at least you remember now in your secondary years here 4, you see a rod cutting across the field. The faster you cut, the higher the EMF.
So what is delta V?
Sorry, delta V is the potential difference. That means if I were to put a voltmeter across, this will be the volt that I measure.
What
This
is
the volts that I measure.
I thought it should be the potential difference before the movement and during the movement. Rather than
measure
the two-
equilibrium.
Does that the best also?
What I measure is the equilibrium. The equilibrium B.
Oh.
The movement is in split seconds, microseconds. You won't be able to see the build-up unless you've got an oscilloscope. You can
Understood.
measure to microscope. Microseconds are.
But just to clarify, it's not actually the potential difference between two ends of the rod. No.
Then what will be the potential difference be? Well, where would it be across?
I-
It is across the two ends of the rod.
Oh. Okay.
It is between two ends. But of course, if you want to really open this section up, right, there's actually a whole, there's actually these positive charges over here, there's negative charges over here. So if you want to consider this microscopic range, there is a potential difference across it even. But what we are focusing is the potential difference across point X and point Y. This point and this point, the ends of the rod.
Okay.
But there is certain interesting physics happening inside the layer of charges. You're correct. That one you need Gauss law and other principle to understand what's the potential difference across this layer and what affects the thickness of the layer of charges. Interesting things to think about. Cool? Okay, now I'll just like you to have a feel of the numbers. So let's try. Yeah. So if I were to pull a rod across at 15 meters per second, a rod that is, say, for example, 60 centimeters, and in the magnetic field there is Earth's magnetic field. So 4.0 times 10 to the power minus 7 Tesla. Give it a try. Just play the numbers, get a feel of the order of magnitude that you're talking about. Give it a try.
15 times 4.
Yeah, you have to go right. Remember to watch the video.
Sir, 60 centimeters.
60 centimeters. Yes.
Okay.
So what is
Your point.
Again, finding the potential difference across the rod. Yeah, induced. Find the PV across the rod.
It's very small.
How small? What's the value?
3.6 times 10 to the power of negative 6, I guess.
6 volts.
Yeah.
This is roughly the Earth's magnetic field. So that's the reason why if you hold a metal rod and run across the field, you don't get electrocuted.
Like what I'm doing now.
Kind of. And in fact, 15 meters per second is actually quite fast.
Yeah,
15
that's true.
meters per second times 3.6 is about 50 km per hour.
Like that.
It's actually quite fast. At 60 centimeters, you just run along like this, right? Or you take a rod and stick out your father's car and it still doesn't get electrocuted, so don't have to worry. Yeah. But in the frontier of space exploration, some satellite actually what they do is that they actually dangle a really 100 meters, 200 meters long wire, and because the satellites
for
are
them
moving
to
at
slow down.
7,000 meters per second, remember?
So,
You have 7,000 meters per second, 7 km per second, about that. So we're talking about many times more than this, many times more than this. So even though the magnetic field is weak, it still generates a substantial amount to charge the whatever device.
but kinetic energy will be lost.
Then
Then the satellite will fall into Earth.
but
Then
satellite
GG.
itself usually have their own booster
Oh.
to keep it a kick. So I'm sure that people will have made the calculation.
Then why spend the energy to to a big way.
Energy generation process. So if you were to use the heat to generate electricity, there is other mechanism that you need to feed. As opposed to just dangling a wire, I think it's so much simpler.
So save more components.
Yes, simpler components. And in space, any maintenance is not like they call plumber, hello, plumber.com.
Yeah,
you need to send another rocket out there to repair. So you try to keep it as simple as possible. Okay? So, just to give you a value, yeah? Remember, whenever you see equations, try to have a sense. It's important to have a sense of the values that we're talking about. Next one. Next. We still haven't answered the question, how on earth is this related to flux linkage? And what on earth is flux linkage? Then you have magnetic flux density, you have magnetic flux, so you're going to feel magnetic flux linkage. It's like, what the flux? Yeah. Yeah. So how? What are all these things? Sure, we'll come to that. Yeah. So let's develop from here. Okay. I got a rod moving across a magnetic field, and then this is length L. Can you see that delta V being equals to VLV? V can be written as x for time. Displacement per unit time, right? So this is B Lx upon time. What is L times x? Do you agree that it is the area swept? Now, if I put this in the perspective of a loop, say for example, can you see that it is the decrease in the area of the loop? Not just the area of the loop, it is the decrease in area of the loop. Previously it was here, now it is here. If I move my rod to this position. So it is a decrease, it is just change in area. So therefore, it is. If we throw the bead into this equation, we call this thing change in magnetic flux. So we call BA magnetic flux. It's just redefining it. Now what does magnetic flux mean then? Now let's come back up. Let's try to think about what does B mean. Yeah, if I got a field strength, right? So if I got a field that looks like this versus a field that looks like this, which one is stronger, X or Y? X. So we say that B of X is bigger than B of Y, right? So B has to do with, the term that we use is magnetic field strength. But actually physically, if you represent it in diagrams, it is the density of field lines. It is the density of field lines. Now if you take the density of field lines across an area times the area, what do you have?
Total number.
Number of field lines passing through. So the physical meaning, or layman understanding is, this represents the number of field lines passing through an area. So I can have a weak field captured by a big area, the flux will be the same as a very strong field captured by a small area. It's the number of field lines captured. Okay, very important ideas. Now I don't think this is captured in your notes. You might want to just capture this point over here, somewhere near BA, and I think in your notes it says cos theta, flux linkage. In a lesson that follows tomorrow, I will give you a table to summarize the difference between flux linkage, flux, and flux density. So now I'm just giving you pockets of knowledge. There is still an unanswered question. And I two unanswered questions. Just now, what Zane said was, Faraday's law states that the EMF induced is directly proportional to the rate of change of magnetic flux density, flux linkage. What is this? Is this magnetic flux linkage or magnetic flux? There is a difference. And I'll explain to you what's the difference, yeah? In time to come. But before I answer that flux and flux linkage difference, let me ask you another question that will lead on to that. Does this depend on orientation of the coil? So say for example, if I have a coil that looks like this, and a magnetic field that points down, does it matter in terms of the number of field lines captured by the coil if I orientate it this way or this way?
Sorry, what again?
If the field were to point down, does it matter in terms of the number of field lines captured when I orientate the coil this way or this way or this way? Obviously it does, right? So do you see that there is a missing piece over here? This doesn't have the angle.
another sine or cosine.
Yeah, correct. So the full formula, this is basic understanding. The full formula or the full representation of flux is this, which is equals to B A cos theta.
Oh.
At this point, I'd like to just check with Nico. Can you see that thing over there? Does he see all the way there?
No.
Okay, probably you should just tilt the thing a bit until you like, and then
Okay.
Yeah. Yeah. Okay. Good. So you must see because our friend over there you can see. So this angle theta over here represents. You must be very careful. The angle between, this is going to be a little bit mouthful. The magnetic field strength and the normal to the area.
Wait, so you mean
Actually, it is B
This?
dot A.
so this thing?
Yeah. Okay. So if I got an area, a field, it is this angle.
Yeah. So if that we use that diagram, it's like moving this way.
This one is the normal is this way.
Yeah. So
Yeah.
so
And the field is also this way, so the angle is 0.
it's like this.
The angle is 0 in that case. So it's cos 0, which is 1.
My question is, sir, if I change value of theta, it's like to this.
Yes, if you orientate. So in this case over here, the coil is now like this. The field is now like this. Yeah. So if I orientate the coil this way, then the normal will be here to here. So it will
So
change
move.
the angle.
Okay.
So now we're slowly developing the idea that no, we can induce EMF without any motion of the rod. We can just rotate. We can change the flux linkage, right? Just now we talked about movement. Now we talk about rotation. We can also induce. We talked about even no motion. I change the magnetic field, also got induced EMF. So there are 3 ways I can induce EMF. I can change the B, I can change the A, or I can change theta. So we are broadening our idea now from just movement, from BQB.
Interesting.
Cool, can. So not enough, still not enough, just saying, still not enough because we haven't gone to flux linkage yet. We're still at flux. Yes.
So, but when you're talking about B, right, the direction of B, wouldn't it always be in the direction of the area?
No. Like say for example this one, I got the direction of the B, which is here. B is here, but the area vector is here. So what I'm doing when I take apart the equation, I take B cos theta. Which part of the field do I take? B cos theta is this one. Again, perpendicular to the area. This is B cos theta, this is B sin theta. So if we take apart the equation, we take B cos theta times A. What I'm doing is to resolve the field that is perpendicular to the area. That's what I'm doing. And you have done vectors, right? So you know area has a vector. The area R dot N. R dot N equals the number. Remember that one? Yeah. So area has a vector. The area vector. Sorry? A is the plate, the area of this one. Yes, correct. The area of this one. Okay, so now we're going to move from here. Now we're more or less there already. 90% down already. We just need a 10%. Let's take the 10% now. Okay.
I still wonder why that question you.
Can you see that what we're doing over here is only for one coil, one turn? Right? One turn only, alright, one coil. So what if I have multiple coils? So if I have one coil over here, next coil over here, next coil over here, and I have a magnetic field over here.
Sir, it isn't even straight.
Solenoid.
We only consider the straight.
But area, I know part of my derivation, I say that it has to be straight.
No, I mean
In
the
fact,
math.
if it is a circular area, if you cut it into small little sections, every section is straight.
So pi equals to 4?
Integral.
So pi equals to 4?
So in general, what I'm saying over here, this area need not be square.
Okay.
It is the area of the loop or change of the area of the loop.
But the math will be quite crazy.
A little bit, yes. But of course, if we give you a question, it should not need integration. It should be simple case. No worries, I'll give you examples. You'll see how simple and how manageable it is. And I'll also show you examples of how unmanageable it is.
Okay.
Certain situations. Yeah, I can tweak the situation. Now, if I were to have 3 coils, can you see that if EMF is induced in such a way where for coil 1, I have a positive N over here, negative N over here. For coil 2, it is almost identical. So it should have a positive, negative, and again positive, negative. So can you see that if I connect the 3 coils together, it is like this situation here, plus, minus, plus, minus, plus, minus. So if each EMF is E, can you see that the total EMF induced is 3E? So can you see something missing over here that we haven't taken into account?
Number of coils.
Excellent. Correct. So the difference between flux, which is VA cos theta, and flux linkage, it looks like green lantern, VAN cos theta. And Faraday's law says that it is the rate of change of magnetic flux. Linkage. Not flux, it's flux, linkage. Because as you can see, N obviously matters. Obviously matters. So it is wrong if you say flux. Rate of change of flux. It's rate of change of flux linkage. And although N is the one that we seldom change, how do you change the number of turns of coil? Usually change B, change A, or change theta. In generators, we change theta, we rotate the thing. Yeah. Okay. We got 10 minutes. Let's try simple questions to get ourselves started. Simple. Warm up. Simple to me, simple to you. Cannot. At this point of time, any questions you'd like to ask? Let me just do a quick summary. I went from a rod moving, I linked up E and B field, and then I show you how it can be used to derive delta V equals to BLV. And then I went from BLV to show you how it is linked to magnetic flux linkage, this one. And then I show you that this is not sufficient, we need an angular dependence. And then this is not sufficient again because the number of turns affects the number of amount of EMF. So eventually, the rate of change of flux linkage is proportional to the EMF. Okay. Let's try one question. If we got extra time, enough time before 10:20, then I'll show you the answers. Okay. Okay. Still alive, huh? Let's see whether you can handle this. This is initial, this is final. So I have a situation where I have a coil with number of turns 50 turns with diameter equals to 60 centimeters, and I've got a magnetic field strength that is 60 millitesla. It rotates from this position to this position.
Oh, so you mean this way?
Yeah, it goes from here to here. Is there flux linkage change? Yes. Due to what?
The
Which
sine,
the quantities?
the cosine theta.
N or theta, correct. So you have to be clear already. Whenever you see a change that induces EMF in your mind, you ask, is it V, A, N, or theta? Okay? So we've grasped the theta already, so okay, good. So theta is the one that changed. Therefore, my question is, if the change is made in 250 milliseconds, I would like you to find the delta V induced.
Okay.
Let me give you some guidance. It is delta flux linkage over delta T, which is equals to flux linkage final minus flux linkage initial over T. Now you do the plugging in numbers. You need to operate this. B, A, N are all constant. It's just the theta that change.
Oh.
Theta, remember this? Theta is the angle between the normal to the area and the field. So where on earth, for initial, let's say for initial.
But the area is like two moon shape.
Okay, this is the problem of representing 3D on a 2D platform. So initial, okay, basically the area is like this. The field initially is like this. Then 2.
Yeah, so the change of area is
So
like this shape.
there is no change in area. There is no change in the field strength. There is no change in the number of turns. What I'm changing is the angle. Now let's talk about this. Let's break this out in final and initial. If I realize I didn't give you something. I realize I didn't give you the angle. Let's say if this is, if you're a bit more kind, I'll give you this as 30 degrees. Yeah? Yeah. Or probably even more kind, 60, like you understand why 60 is more kind. Yeah? Yeah, because cos 60 is yeah. So if I have a field like this and then I move like this, what's the initial angle for the initial position? What's the theta for the initial? 60. And for the final?
0.
0. initial angle is 60, final angle is 0. Now I understand the change. I'm so confused.
Actually, sir,
It's not given.
my question is, since essentially it's a change of the area
Yep.
covered by the coil, so initially, if we view from the direction of that magnetic field line, the round coil actually looks like this shape. And then after the rotation, it's a perfectly round shape. So
You can
actually, the
see
change
that.
of
Now I understand your perspective. You're talking about a change in the area itself.
yeah. So
From the
this is
perspective
really confusing.
It's not wrong, just that it's a little more difficult to perceive for some people that there is a change in area from the perspective of the field.
My question is, then how can we still just simply use cosine theta? That's why at first I asked it's not even a straight rod, because for straight rod it's understandable. But
That's also the reason why I did not start off with this, because it is actually quite difficult to understand what exactly happens when you actually have a change in the flux linkage, why it induces EMF at all. That's why I started with something about motion. If you actually ask me about why actually physically what changed when I changed the angle, why does it actually induce EMF? What I can say is, as you change this, you agree that the magnetic field actually starts to cut the sections.
yeah,
As it rotates inward, it starts to cut the rod. So the cutting of the magnetic field across the rod actually causes the EMF. Because the rod cannot tell whether it is moving through the B field or whether the B field is moving through it.
yeah, it's the same.
It's
But
the same, correct? So to the rod, it feels as though that it is a rod or sections of the circle, small little rods going through the field.
but it's like each point is moving at different speed.
That's right. So if you do all the integral sum,
Yeah, I'm super confused. But then how can that simple equation still apply? It's as if we are dealing with a nonlinear.
The beauty of it is that it still applies. Let's take a look at this, yeah? Let's take a look at this. A curved rod now, moving across the B field. This is V, and then the B is still the same.
So this is understandable lah. Each point is moving at the same
So
speed.
if you talk about this, if it is a curved rod, you'll find that the effect is the same as
As a
this
straight
rod.
rod,
Yes,
yeah.
right. So if you look at this, the idea is to say that if in a curved situation, general curve situation, you can break it down into the rod's length that is perpendicular to the velocity. Something I'll explore a little bit more. You think about this case, even if I have situations where I got a rod moving, say a rod just down, I got a field over here, what if I were to move the rod this way? What if I got a situation like this, and then what if I got a situation where the rod is tilted and I pull it this way?
Oh,
It's
it's the
good to
same.
think about. But I jumped the whole process to just give you the clue since you asked the question. If you have a curved rod and move this way, if you do the integration of all the induced EMF across this small little
Add
rod,
up to be a straight
it will
rod.
be that straight rod. The length effective that is perpendicular to the velocity. For those of you who are lost, it's normal. This part is normal, yeah, because I'm jumping some steps.
So we don't have to find a place.
Yes.
So when you move a rod, right, as long as the rod is like stationary in terms of omega, right, doesn't rotate, right, there will be no change in magnetic.
There will be induced EMF.
There will be induced EMF, but then it will not change, right?
Yes. You see, if you talk about a rod and you rotate this rod, right, it's meaningless for you to talk about flux linkage because there's no area enclosed. So we fall back to the BLV. For rod, you use
Talking about
BLV.
this particular example.
This one?
When you're moving this rod, right?
Yes.
And you don't
You mean this rod or the curved rod?
the straight rod.
The straight rod, yes.
If you're just moving it in that direction, it doesn't rotate, right?
Yep.
Will there won't be any change in flux of flux?
No, because if you talk about a rod, it's meaningless to talk about flux linkage per se. Because flux linkage and flux, you always have to talk about loop. So for rods, usually you fall back to BLV. Yes, correct. So there are two tracks over here. The reason why I want to go through this development is because you slowly see that there are two kinds of questions. One on rods, one on loops. Loops doesn't matter whether it's triangular, rectangular, or circular. It's always changing BAN formula. Rods, it will always go back to BLV. So there are two kinds of questions. Yeah.
But for BAA, what is A actually?
A is the area. So for this case, it's pi r squared.
Oh, okay.
Circular. I think it's circular, right?
Oh no.
That's the problem of 3D or 2D.
So it's just
Can someone tell me what's the number?
change will be
Anyone?
0.0,
0 point?
0.06 times 60 times 0.09.
0.6
Okay, what? Say that loudly.
times 1.06
1.06. Oh.
No, 1.696. So it is 1.7.
divided by 0.25.
So one has to be wrong, or one has to be correct. Let's be more positive on it.
Times
Derek 1.7.
Oh, there it is right.
No. Okay, let's confirm. 5 times 0.3 squared times
So I wonder how you define
minus 3 times 0.5 divided by 0.25. I got 1.7. Yeah.
so I wonder how you define speed speed of
Speed of rotation.
yeah how do you
You
define that?
are surfacing a very good question, which is actually a question I wanted you to think about as a class. But let them get the 1.7 first. Okay? Let them get the 1.7. For those of you who have already gotten 1.7, what I want you to think about this is this. If I were to plot the EMF against time, is it always 1.7? If I somehow can track the EMF across time at within the 250 milliseconds, is it going to be always 1.7? Or is it?
But the final will be
Yeah. The
final will be I mean
the
between the
average
initial
EMF induced is 1.7.
oh
Yeah.
yeah
Okay. So you think about this, we have time's up already, so we will discuss few situation. This one first. Is it average? How does it vary? Then this one we're going to discuss this kind of situation. Variations from the norm.
I think it's like this the shape.
We will discuss this. I'll hold your hold your suspend you first. Can you press the stop button? Thank you.